Hello everyone, welcome to Geometry of Data. This is the first of the video lectures that we'll be releasing. There will be two of these this week instead of our regular classes. I'll try to sort of write everything out in the screen so that you can work through it with me and sort of we can learn together. And if you have any questions, you can then sort of email us or post it on Piazza and we'll address the questions there. All right. So in this lecture, we will cover some manifold topics first. Then we will do neural networks, what neural networks are, basic MLPs, activation functions, and everything related to basic neural networks. And then after that, we will see how these neural networks connect to the manifold math that we do in the first part of the lecture. And then we'll see some examples with that. And then we'll see some specific kinds of neural networks through the end of this lecture and the next lecture to see how they can be used for different aspects of the manifold math and manifold learning problems that we have seen so far in this lecture. Okay, so the first topic that we need to learn about is immersion, right? So immersion is a property that is defined for mapping functions between manifolds. Okay, so let's define some manifolds first. Let's say we have a manifold M as such and a manifold N like this and a mapping function between these two manifolds psi. Recall that for any point x we can also draw the coordinate map um, which is the tangent plane uh, at that point and represent it in a lower dimension coordinate chart, right? So we a point on this manifold moving in this direction can be represented in the coordinate chart to be moving as such, right? Similarly, let's say we have a tangent space at this point, which is the image of the point x through the function mapping function psi. So this is psi of x. We have a tangent plane here, which is mapped in another coordinate system as such. Okay, all of this is from previous lectures. This is a different coordinate system. Let me draw some coordinate lines. Okay, great. So far we have a manifold M with, let's say, the dimensionality of a small m. So dimension of manifold M is equal to small m. And similarly, the dimension of the manifold N is small n, right? And we have a mapping function. Let's say that this mapping function is smooth between the manifold M and the manifold N. Now, let's assume that the dimension of the source manifold capital M is less than or equal to the target manifold of the mapping function N. So if we have a smooth mapping function psi between a manifold M of dimensionality N M and to another manifold of a higher or equal dimensionality N, if we have a map like this, we can define the property of immersion for such a map. If you go from a lower dimension manifold to a higher dimension manifold, immersion is a property which can be defined for maps that go from like a lower dimension manifold to a higher dimension manifold. Okay. Um, let's also just establish that between these coordinate maps, you also have a transition function, like a mapping function, which is represented by the derivative of your mapping function, right? Because this is the tangent space Tx of the manifold M, and this is the tangent space which is denoted as T mu of x at the point mu of x on the manifold N. Okay, so there's a mapping function between the coordinate representations of these two tangent spaces also, and that mapping function is represented as the derivative of the original mapping function. Okay, so now let's define what immersion means, right? So given all of this, like given manifolds M and N, a smooth mapping psi which goes from M to N is called an immersion if this derivative of the mapping function that we defined, if this map which goes from this tangent space to the target tangent space which is around the image of the point x in the manifold N is injective, right? Is injective for all x in the manifold M. Okay, so what we want is that this mapping function, which goes from a lower dimensional manifold to a higher dimensional manifold, if that mapping function is injective, and also the derivative mapping function, which goes from the tangent space of M to the tangent space of N, is injective, right? And now, what do we mean by injective, right? So, like a very basic example for injective functions is that, let's say you have a set A which has a bunch of points and a set B which is a certain number of points. If a function is defined between these two sets, if every point in the source and this is the target, that's and these are the mappings. So if the mapping function can find in the source domain every point is mapped to a unique point in the target domain, then this map is called an injective map, right? So essentially what we want is that the target domain should not have multiple points mapped to the same point, right? So we want a unique point to be found in the target domain for every point in the source domain. So such a map is called an injective map. But how do we check this injective property for a general mapping function between two manifolds, right? That is what we need to see. So let's remove this. Now that we know what injective functions are, how do we check if a function is injective or not? So let's just write the mapping function psi in all the coordinates, right? So psi can be operated on all of these coordinates of the source manifold, so m dimensional. And because the target is as target manifold is n dimensional, we can write this as a matrix where every row is a different dimension of the target manifold. So you go from psi 1 to psi n, and the coordinates of x's go from x1 to xm. So we get a matrix like this. Now let's see what d psi of x would look like. Okay, so d psi of x would be is just the Jacobian of this transition function, which is the first coordinate, uh, sorry, derivative with respect to the first coordinate, derivative of psi 1 with respect to the second coordinate, dot dot dot, derivative of psi 1 with respect to the last coordinate of the source manifold. And similarly, we have derivative of psi n with respect to the first coordinate, and so on, derivative of psi n with respect to derivative of x m, right? So we get this manifold. Now note that this is in cross m Jacobian, right? Now for the mapping function psi to be injective for psi which goes from m to n to be injective, we want the rank of this Jacobian matrix that we found, d psi x, should be equal to m, which is the dimensionality of the manifold that the mapping function is defined from. Okay, and what does this mean even more, in even more simple terms, is that it means that the columns of the Jacobian are linearly independent. Okay, right? So just a quick recap. What we want is that to define a property about smooth mapping functions from a m-dimensional manifold to an n-dimensional manifold when m is less than n, right? So we're defining immersion as a property of a mapping function which goes from a lower dimensional manifold to an equal or a higher dimensional manifold. Now, this mapping function is called an immersion if this mapping function is injective and the derivative of this mapping function, which goes from the tangent space of M to the tangent space of N, is also injective. And to show that this map is injective, what we do is that we find Jacobian matrix, and then we have to show that the rank of the Jacobian is equal to M, right? And that establishes this mapping function psi as an immersion between the manifold M and N. Now let's look at some examples of this. Okay, examples. Let's say we have a mapping function psi which goes from R to R2, right? So from one dimension to two dimension. And this function psi is defined as x comma x square, right? So it takes in one value, 1D, and it gives us two values, 2D, right? So let's draw this function. We know from our coordinate geometry that this function looks like this. This is psi of x, and let's say the coordinate system here is y1, y2. Okay, now does this satisfy the immersion property? So for this to satisfy the immersion property, for this to be an immersion, we want the d of mu x should be rank 1, right? 1 because m is 1 here. M, m, right? So let's see what d psi x looks like. D psi x here would be the first, sorry, the derivative of the first coordinate, which will be dx by dx, and the second one is dx square by dx, right? And this will be 1 2x. Okay, and we can see that the rank of this is equal to uh, 1. Therefore this is an immersion. Alright, so an easy example to see how we find if a function is immersion or not. This function goes from 1 dimensions to 2 dimensions, so m equals 1 and n equals 2. The function is very simply defined as this parabola x comma x square. We find the Jacobian of this function, and then we see that the rank of the Jacobian is equal to 1, which is equal to m. So we say that this function is an immersion, right? Now let's look at another example. Here, the function psi x again goes from R to R2. We are choosing R and R2 because it's easier to draw and we can visualize it better here on paper. In this one, let's define this function as x cube comma x square. Okay, so, and let me plot this function. This function would look something like this. Okay, this is what psi of x looks like. Y1, Y2. Okay, and let's write the Jacobian. This is equal to 3x square and 2x. Okay, now you can see here that these columns are not linearly independent because both of them will go to 0 for value for x equal to 0. So this Jacobian sort of degenerates around 0. And we can see that in the plot as well that the tangent at 0 is not defined because here you can have two directions which sort of map to the same point, and yeah, and which is why this is not an immersion. Okay, yeah, so this was not an immersion. Let's look at one more example. Psi of x again goes from R to R2. This time let's define it as cube minus 4x. You'll see why we have such a complex definition, because we want a specific plot. And the Jacobian here, I'm writing it out directly, is 3x square minus 4 and 2x. And this looks like something. Okay, yeah, y1 can two, this is x. Okay, okay, so here you can see that this satisfies the emergent property in as far as it is not possible to get a 0 comma 0 transpose vector for any value of x. So this will never give a 0 comma 0 vector for any value of x. So as far as that is concerned, we have that property satisfied. But however, if you look at the plot, there is self-intersect. Oh, I'm sorry. Let's bring that back. So if you look at the plot, there is self-intersection that happens in this map, which sort of indicates that this itself is not really a manifold. So this is not a manifold. So in which case, even though we have the other emergent property satisfied, just because there is self-intersection and it's not really a properly defined manifold, this is not a case for immersion. All right, right. So that was immersion. Now let's look at submersion. Okay, it's a similar concept, but submersion is defined between two manifolds if the mapping function is going from a higher dimension manifold to a lower dimension manifold. Okay, so in immersion we had the function going from lower dimension manifold to an equal or higher dimension manifold. For submersion we want it to be an equal or lower dimension manifold, right? So let me just draw these manifolds here. So this is n. On the manifold M, we have a coordinate chart, the tangent space at the point X, and the mapping between this tangent space to the tangent space here, just this at the point which is the image of the point X through the mapping function, like this, is called d mu. Oh, sorry, the point X, right? So we go from manifold M to N. Here we want M to be greater than or equal to N, right? So similarly, what we want is that given manifolds M and N with dimension of M being greater than or equal to dimension of N, and smooth map is called a submersion if this map I is surjective, which means onto, and the derivative of the function which goes from the tangent space of M to the tangent space of N at the point psi of x is also surjective for all x in, right? This is what we want for a submersion. It's similar to the immersion concept, but here what we are doing is we're going from a higher dimension manifold to a lower dimension manifold. right? So for this to be a surjective mapping, we want d of mu x is the Jacobian, by the way, just to recall, is the Jacobian matrix, and it should be maximal rank, right? And by maximal rank, I mean that the rank of this Jacobian should be equal to, right? Which is the dimensionality of the target manifold. All right, so let's look at some examples. In this case, we will not derive the Jacobians and just see all of them in math like we did before. I'll just draw some examples and you can sort of, in your own time, derive what the Jacobians will look like and if it is maximal or not. Okay, so let's say this is M and the surface is defined as x square plus y square minus c square equals 1, and the mapping function is going to a lower dimensional manifold which is just S1. It's the spherical manifold in one dimension, right? So you need to see if this is maximal ranked or not. And for that, you have to find the Jacobian function and then get the rank of the Jacobian function and see if it's equal to n or not. And n is equals to 1 here, right? Okay, another example is this. Draw it carefully. Yeah, and this sort of extends like this. And the same thing upside down over here. And this sort of extends to infinity as well, like in all directions. Okay, and this is defined by the function x squared plus y squared minus c squared equals minus 1, and the mapping is between this manifold to R2, right? So you need to check if these two are examples of submersions or not. All right, so that was submersion. After this, we'll study. Now, the next topic that we'll look at is neural networks. What we will do is that we will first sort of look at the basics of what a neural network is. How do we construct neural networks? What is it made up of? How do we train it? What are activation functions? Things like that. And then at the end, we will see how neural network layers that process the data from the input layer to the final layer, these intermediate layers, how they can be understood as either submersions or immersions, and that we saw right now. Okay, so as far as neural networks are concerned, let's first look at how these neural networks came about and what is the motivation and how, like, what is it based on. Okay, so neural networks were essentially sort of designed to mimic real neurons like in the human brain, but the way it's sort of formalized in math is not really at all how the brain functions, but still the inspiration came from that. So let's look at what the inspiration was. So let's look at what a typical biological neuron looks like. Okay, so pardon my drawing, but a biological neuron essentially is made up of a cell body and an axon, which is like a thin wire which is connecting it to the root of this neuron. These are called terminal, this is called the terminal bulb, whereas the endings here that come out of the cell body, these are called the dendrites. And what happens is that a neuron receives a signal in the terminal bulb from another neuron that's connected, whose dendrites are connected to the terminal bulb here. And once you receive a signal, this the signal passes through the axon and then gets processed and gets passed around through the dendrites. So this is what like a biological neuron looks like. How does it work? Like, how does it get activated? Is let's look at that a little bit so that we understand what the inspiration for like a mathematical neuron is and how we understand the activation function in our brain, right? So let's like this is a plot of this is just like a graphical interpretation of the action potential and the threshold that they need to attain in order to send a signal down the axon, right? So to in order to send a signal through the axon, the stimulus needs to be of a certain strength, and if that strength is above the threshold, the signal then gets transmitted through the axon, and we say that the neuron is activated, right? So let's look at a graph that sort of shows this a little bit more clearly. So let's say on the x-axis we have time in milliseconds, and on the y-axis we have voltage, which is measured in millivolts. And yeah, and this is the voltage that you measure from an axon, so that you measure from like in a neuron. So this is the amount of voltage passing through the neuron, and let's say this is the resting potential, this is the resting stage, rest. So initially, when there is no stimulus, the voltage is on the resting stage. So we are here. Let me change the color of the pencil. So that sorry. Okay, so when there is no stimulus, the voltage is zero. Then let's say you get a stimulus, but the strength of the stimulus is not strong enough, so you don't really pass the threshold. So the voltage will increase and then decrease again. So this is not an activation because the strength of the signal was not above the threshold. And let's say this is what the threshold is. Let's define this as the threshold. So the strength of the stimulus needs to cross this threshold, and once it does cross this threshold, let's say you get a strong enough signal, the activation goes beyond the threshold, and then you see a spike in the voltage. The spike then comes down. There is a refractory period in which the neuron sort of recovers, and then the voltage goes back to the resting stage. Right. So this is what an activation looks like in a biological neuron. This is the action potential. The peak is the action potential. This stage is called the depolarization stage, and this stage is called the repolarization stage, right? And any stimulus that you get below the threshold is not really an activation. Okay, so this is what an activation looks like in the brain. So essentially what you're doing is that you're getting a bunch of signals from different sources, and if those signals sort of pass a certain threshold, are above a threshold, you see a spike in the voltage in the neuron, which means that there is some activation that has happened in the neuron. So we call that as an activated neuron if it passes a certain threshold. Now, having this as an inspiration, let's see what a mathematical neuron looks like. Okay, right. Uh, okay, so let's say we have three inputs: x1, input x2, and value x3, right? And we have these three inputs going into our neuron. Okay, and the neuron, given these inputs, gives us an output y, right? So this is the input, this is the output. Now what is happening at the neuron? So if you recall from the intuition that we got from the biological neuron, what needs to happen is that given these inputs, if the value of the input or the strength of the input is beyond a certain threshold, then this neuron should get activated and it should give us a signal. And if it is below a certain threshold, then they should not get activated, right? So that is all that we want, is that it should process the input and somehow take the input into account and then give us an output. Okay, right. So for each input, this neuron has a weight which it corresponds with the number of inputs. So this x1 connection with the neuron has weight w1. This x2 connection, let's say, has weight w2, and similarly this has weight w3. So the operation that is happening in the neuron is just a weighted summation of all the inputs. So we have a summation of I goes from 1 to n, where n is the number of inputs. Here we see that n is equal to 3, but given any number of inputs, the summation goes over all of the inputs. Okay, so summation goes from I equal to 1 to n, and we multiply the weight with the value of the input which corresponds to it, and then we pass this value through an activation function. Now, the threshold that we talked about, thresholding, is that the value of these inputs should be higher than the threshold, is done by this activation function, right? Which sort of adds a non-linearity to all of this, and this sort of gives you a mathematical output to give to a certain number of inputs. So given three inputs, we would multiply each of these values with a corresponding weight value, sum them up, and then pass them through a nonlinear activation function, and that is what the output of this neuron would be. So yeah, so you can see how we sort of came about defining a mathematical neuron using the same intuition that is understood from a biological neuron. Okay, so notice that this one neuron, which is a function that takes in n inputs and gives out one value, is a mapping function that goes from r n to a real number r, right? Because there are n inputs here, and then it gives you one value, which is y. So it goes from r into r. And if we sort of write the math, like expand out what the operation is, so the input can be written as x, which um, sort of gets acted on by these weights, which is w11, w12 to w1n, right? So there is one weight for each value in x, and we multiply these by all the values of x11, x12 up to x1n, and this is wait times the input, and what we get is w11 x1 plus w12 x2 w1 xn, right? And this can be represented as w time x plus b, which is on the real line, and this x is an element of Rn, right? So this is how we represent a neural network. After this operation, we also pass this value through an activation function, and we'll see some activation functions in a little bit. Before that, let's see how we use these neurons and sort of arrange them together and place them together to form neural networks, right? So, for example, let's say, what is a neural network first? Okay, so a neural network is a series of layers where okay. So essentially what we do is that we stack these neurons into a bunch of layers. So for example, let's say the input layer, which is the first layer of a neural network, the first layer is always called the input layer because the input directly goes into this layer. So let's call this the input layer. Let's say it has three neurons, and then every intermediate layer, which is not the output layer or the input layer, is called a hidden layer of a neural network. We call it hidden because the activations in these layers do not really sort of mean anything. Um, but you can have as many hidden layers as you want. So the deeper the network is, more is the number of hidden layers that it has. So let's design this neural network with two hidden layers. So the input layer, then hidden layer 1, then hidden layer 2, and then we have an output layer. Okay. Now each of these layers can have any number of neurons based on your choice of the network architecture. Given a certain number of neurons in each layer, what happens is that in a feed-forward neural network, each neuron receives input from each other uh, neuron in the previous layer. So every neuron in hidden layer 1 will get inputs from each neuron from the previous layer. So the previous layer was the input layer. So all of these values will go in to all of these neurons, right? And each of these neurons have the same mathematical function that we just saw for a neuron. So what will happen is that this neuron will take into account um, every value. Yeah, so this neuron in hidden layer 1 will take in values from each of these input layers, apply the function that we saw here as such, and if this value is sort of above a threshold, or whatever the activation function is, so the threshold depends on the activation function. So whatever the value is, the linear combination of all the inputs plus a bias term, and then pass through an activation will be transmitted through this neuron in the hidden layer to the following layers. So if this will go into each layer in the next hidden layer, and this happens with each of the neurons. So similarly, for the second neuron in the hidden layer, we'll take inputs from each of the neurons in the input layer, perform the neuron action, which is the mathematical function that we saw in the just a minute ago, and then the output is sort of transmitted to every other neuron in the following layer, right? So this is how a neural network is constructed. A series of such layers, the deeper it is, the deeper your architecture is, and the capability of the neural network to process more complex data increases with the depth, and also increases with the width of the network. The width of the network is defined as how many neurons does the network have in each layer. So the width of the network at hidden layer 1 is 1, 2, 3, 4, 5 because it has 5 neurons here, and the width of hidden layer 2 is 4 neurons. Similarly, what will happen at the output layer is that this output neuron will receive inputs from every other neuron in the previous layer, and this will also sort of perform the mathematical function that we saw for a neuron and then give an output. Generally, in the output layer, based on what the task is, the activation function is different. Um, okay, so now let's look at some activation functions that we talked about. Recall that every neuron is acting linearly on the input using the weight matrix, and then the output goes through an activation function. This activation function is the nonlinearity, which adds a nonlinear component to these neural networks. And let's see what different activation functions look like. Activation functions. Okay, so one of the most common activation functions that is used is called the sigmoid activation function. Sigmoid activation function, and let me draw what this looks like. So this function goes from let me draw it out properly actually. Okay, so this function looks something like this, right? And this is sort of thresholded at the value 1, right? So yeah, it doesn't go above it, it just sort of touches this value between 0 and 1, and this is where it intersects um, with the y-axis, and this point is 0.5, right? And this is your origin, this is the positive axis, 2 4 dot, this is the minus 2 minus 4, right? So, and this is the value of the input, and this is what the activation output is. So you'll see what that this activation function is useful because it always exists between 0 to 1. So it's constrained between 0 and 1, which, if you think about it, is very useful because what we want is that if we want to use a neural network to sort of predict a class, or let's say predict the probability of an event happening, or like the probability of an image being a certain thing, or maybe a certain signal being a certain class. So what we want to do is that we want to get a notion of probability out of these neural networks. So if the neural network is sort of constrained to output values between 0 and 1, that could be useful to interpret it as the probability of something happening when we train these neural networks. So since the probability of anything sort of exists only between the range of 0 and 1, the sigmoid would be a right choice in that case. Another thing about these activation functions is that you can see that this activation function is differentiable. Uh, and what this means is that you can find like a derivative at all points in this activation function, which means that we can use this in neural networks, because when we optimize a neural network using gradient descent, we will need to be able to calculate the derivative across each of the activations and across each of the layers. And if the non-linearity is non-differentiable, the backpropagation would break down. So we want all of these activation functions to be completely differentiable, right? All right. Another activation function that is common is called the rectified linear unit, or ReLU for shorts. It's called the rectified linear unit. And this is also a very commonly used activation function, probably the most used activation function in the world right now, since it is used in almost all of convolutional neural networks, which are CNNs, which are used for predicting images and processing images. Um, let's see what the activation function looks like. So this is the axis, say this is the origin, change the pen. All right. Okay, so this is what the activation function looks like. It's essentially just zero for every value which is negative. So for all negative values, it's always zero. And as soon as it gets a positive value, it just returns that value as it is. So if we write down the function, this activation function, let's say it's R in terms of Z, and then z is this axis, would be equal to max of either 0 or z itself, right? So this line then would be equal to y equals z, right? And this is the y-axis, which is the output. So what we have here is just a linear activation for positive values and no activation for negative values. So the range of this, as we can see, goes from 0 to up to infinity. This is the range of this activation function. And also we can see that the function is differentiable and is also monotonic. So this one um, will always increase with the increase in the value of the signal, unless the value is negative, in which case it's not really outputting any value. So because of this being zero in the negative scale, this is also a non-linearity that you can use for your neural networks. And this has like empirically been shown to work very well with all kinds of neural networks. Okay, and so now that we know about some activation functions as well, let's look at how these neural networks connect with the theory of submergence and emergence, right? So let's say we have a deep, let me change the color quickly. Okay, so let's say we have a deep neural network, right? And this neural network has multiple layers. So let's say the first layer, layer 1, is represented by a function f1, which takes the data from d dimensions, which is the input dimensionality of the data, to k1 dimensions. right? Which means that there are K1 units or neurons in the first hidden layer of the network, and each neuron gives you one output. So after one layer, the data will be in a K1 dimensional space. Similarly, let's say we have another layer, layer 2, represented by function f2, goes from our k1 to our k2, right? And similarly, we have the lth layer in the neural network represented as fl, taking data from our kl minus 1 to our kl. Okay, and the overall neural network can be represented as a composition of all of those individual layers, right? So just fl composed with fl minus 1 composed with dot 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 f2 composed with f1 of x. Yeah, because each of these layers are applied sequentially on the data. So this is the data, you apply f1 layer and then apply f2 layer and then apply f3 layer and so on. So let's look at one specific layer a little bit more in detail. So for layer 1, what is happening is that the data is going from this d-dimensional Euclidean space, which x belongs to the d-dimensional Euclidean space, through this function f to a manifold which we don't know about, but it's embedded in K1 dimensions, right? So what if we want to comment about this being a submersion or an immersion, right? Right. So to be able to comment on if this is submersion or an immersion, let's assume that um, we we have like a okay, so just to comment on whether this is a submersion or immersion, what we need to find is the Jacobian of this transition map, or this function that is going from Rd to Rk minus 1. And it should also be contingent on whether D is less than equal to K1 or D is greater than equal to K1. And both of these are valid. That would decide whether this is a submersion or an immersion. But other than that, what should happen is that for this to be an immersion, that is if, let's say, d1 is greater than k1, dxf, which is the Jacobian, should have rank d, right? So how do we find the Jacobian in this case, right? So for one layer, the function is just defined as an activation function. Let's say we represent the activation function like this, applied over the weight matrix, and the derivative of f with respect to x would just be the derivative of this composition of the activation function with the weight matrix, right? Now, one thing that we have to note is that all of these activation functions that we've seen in neural networks are generally monotonically increasing, right? Mhm. So, because these are monotonically increasing, the the Rank calculation for this function comes down to just calculating the rank of W, right? So overall, what we want to show for this to be an immersion is that does the weight matrix W have rank D or not, right? Okay, and that is relatively easier to calculate. What you just have to do is that you find the weight matrix W, you represent it as a matrix, you then check if that weight matrix has linearly independent columns and how many linearly independent columns does it have. If the rank that you calculate of that weight matrix is equal to D, then you can say that this is an immersion, right? And if we were checking the condition for a submersion, in that case, again, you will have to check whether d is less than equal to k1 or d is greater than equal to k1, and then find the Jacobian and see if the Jacobian satisfies the correct property or not. Okay, so that is how every layer of a neural network can be sort of understood as a submersion or an immersion between manifolds. And yeah, so that's how it connects to the neural network theory. All right, thank you.